Okay, so has GPT-5 actually cracked spatial intelligence? Understanding where things are, mentally rotating shapes, all that stuff.
It's a huge question, right? Because
Oh.
that kind of intelligence, that spatial understanding, it's fundamental if we're ever going to get to AGI, artificial general intelligence.
Absolutely. And AI needs it to, well, operate in the real world like we do. Adapt, interact. It's key.
It really is. Without it, AI is kind of stuck in the digital realm.
And today we're doing a deep dive into a really fascinating new paper. It's called Has GPT-5 Achieved Spatial Intelligence? An Empirical Study. Comes from researchers at SenseTime Research and Nanyang Technological University.
Yeah, and our goal here for you listening in is to really unpack what they found. They put GPT-5 and other big multimodal models through their paces on spatial tasks.
We want to figure out, where do these cutting-edge models actually stand? Are we close to human-level spatial smarts? And what are the big hurdles still ahead for AI researchers, for ML engineers like you?
Definitely. Now, if you just need the quick version, the 1-minute rundown, here are the main takeaways.
Okay, hit us with it.
All right, first, this study shows GPT-5 is showing unprecedented strength in spatial intelligence. It's basically setting a new state-of-the-art, big step up.
Okay, impressive.
But yeah, despite those gains, GPT-5 still falls noticeably short of human performance, especially across a whole range of spatial tasks.
So not quite there yet?
Not quite. The research also pinpoints the specific types of spatial problems that are still the toughest nuts to crack for these models.
Ah, okay. And what about the whole proprietary versus open source thing?
Right, that was maybe one of the most interesting bits. Proprietary models, like GPT-5, they don't seem to have a decisive edge over the open source ones when it comes to those really hard spatial problems. They both struggle similarly.
Huh. Interesting. Okay, so let's dig in deeper. Why is spatial intelligence so critical, more than just a neat AI trick?
Well, think about it. Any AI that needs to interact with the physical world.
Like a robot or a self-driving car.
Exactly. Or even an AI trying to understand, say, an architect's blueprint. It has to understand space. It's fundamental.
Makes sense.
And the thing is, even with all the progress in these multimodal large language models, MLLMs, they often fail, spectacularly sometimes, at spatial tasks that are just dead simple for us humans.
Yeah, the paper had that really striking example, didn't it, in Figure 1?
It did, yeah. It's quite the contrast. GPT-5 can solve these incredibly complex Raven's progressive matrices, stuff that can stump plenty of adults.
Okay.
Yet, it completely messes up things a child could do, like figuring out the top-down view of a few colored blocks stacked together, or a simple 3D rotation.
Wow. So it's like super smart in one abstract way, but struggles with basic physical intuition.
Exactly. It really highlights that spatial intelligence is like a fundamentally distinct skill, and maybe one of the last big frontiers we haven't fully explored in AI.
A fascinating blind spot. And it seems like researchers are really starting to zoom in on this now.
Oh, definitely. The paper mentions that most of the benchmarks they used, and they used 8 different ones, were actually released just within the last 3 months.
Wow, 3 months. That's a rapid acceleration of focus.
It really shows this is becoming a hot area, yes.
So, okay, if spatial intelligence is so complex, how did they even approach evaluating it? How do you break it down?
Good question. They distilled it into 6 fundamental capabilities, kind of like building blocks for spatial understanding.
All right, let's go through them. What's the first one?
First up is metric measurement, or MM. This is basically about the AI inferring 3D dimensions, like how deep something is or how long, just from looking at 2D images.
So understanding scale, like how big things actually are.
Exactly. Understanding physical scale, typical object sizes. They had a task, MM1, asking the model to estimate the height of a garage door in meters. And GPT-5 did relatively well on that kind of basic real-world image.
Okay, understanding size. What comes next?
Next is mental reconstruction, or MISR. This tests the model's ability to understand fine-grained geometry. Can it build a complete 3D structure in its mind from just limited 2D views?
Ah, like mental rotation, or visualizing an object from different angles.
Precisely. Think about interpreting those 3-view engineering drawings. That's MRR. And GPT-5 actually showed strong capabilities here, like in reconstructing an object from multiple views, MR2.
So it can kind of build a 3D model mentally?
It seems so in some cases. It also significantly outperformed an older model in generating novel views, like a top-down perspective, MR3, especially when they cranked up its thinking mode.
Interesting. Okay, so size, mental models. What about how objects relate to each other?
That's Spatial Relations, SR. This is about understanding the relative positions and orientations of different objects within a scene. Where is object A in relation to object B?
Higher, lower, in front, behind.
Exactly. It builds on the first two capabilities. An example task was SR5. Which object is higher in 3D world space, the clock or the house in the back? It requires reasoning about depth and arrangement.
Got it. And what if the viewpoint changes, like the camera moves?
That brings us to perspective taking, or PT. This is about reasoning across different viewpoints. Can the model align what it sees from one angle with what it would see from another, or understand its own movement relative to the scene?
So understanding how the view changes when you move.
Right. It needs a mental 3D scene representation and the ability to reason about those viewpoint changes. An example, PT-6 was figuring out if a camera filming a video was moving left or right based on how the scene changed between frames.
That sounds tough. Okay, 4 down. What about things that aren't just solid, rigid objects, things that bend or fold?
Yeah, that's Deformation and Assembly, or DA. Most AI focuses on rigid shapes, but this capability is about understanding changes, deformations, folding, assembling parts.
Like folding a piece of paper or putting IKEA furniture together? Mentally, at least.
Kind of, yeah. Mentally folding a 2D net into a 3D cube is a classic DA task. Or figuring out how multiple 3D parts fit together. This is super important for embodied AI that needs to actually manipulate things.
Huge implications for robotics there. Okay, one more capability.
The last one is comprehensive reasoning, CR. This is where it all comes together. These tasks require using multiple spatial skills, plus maybe longer memory and multi-step thinking.
So they're really complex spatial puzzles.
Exactly, like task CR9, which seems simple. How many 3D blocks in the image? But some blocks are hidden, partially blocked by others.
So you have to infer the existence of blocks you can't fully see.
Precisely. It needs more than just counting what's visible. It requires spatial inference.
Okay, wow, that's a comprehensive breakdown. But it also sounds like a nightmare to evaluate fairly across different models and all these tasks. How did they manage the methodology?
It was a massive effort. They used 8 different benchmarks, specifically chosen to cover these 6 capabilities. VSI Bench, Sight, MindCube, a whole suite.
And the scale was huge, right? You mentioned tokens earlier.
Yeah, over 1 billion total tokens processed for the evaluation. Just gives you a sense of the computational effort involved.
1 billion tokens. So how did they keep the comparisons fair? Different models might need different prompts, right?
They standardized everything very carefully. Prompts, evaluation methods, metrics. For prompting, they used a zero-shot chain of thought approach for all models.
Zero-shot T. What does that mean in practice?
It means they didn't give the models any examples first. They just instructed them to output their reasoning process before giving the final answer. Like, think step by step, then tell us the answer.
So they could see the model's thinking.
Exactly. It helps performance, but crucially, it gives insights into how the model is trying to solve the problem. The reasoning was wrapped in specific tags, like think and answer.
Clever. And the scoring. How did they avoid models just getting lucky, especially on multiple choice questions?
Good point. For multiple choice, they use chance-adjusted accuracy, or CAA. It mathematically corrects for random guessing, giving a truer score of the model's actual ability.
Okay, so it penalizes lucky guesses.
Right. And for questions needing a numerical answer, like the garage door height, they used mean relative accuracy, MRA, which measures how close the model's answer is to the true value, percentage-wise.
Makes sense. And extracting the answers. Sometimes models give messy outputs.
They had a robust 3-step process for that too. Rule-based matching first, then extended rules, and finally, using another LLM to help extract tricky answers if needed. Really thorough.
It sounds incredibly rigorous. Did they worry about things like position bias and multiple choice? Like, is answer A chosen more often?
They did consider it. There's a technique called circular evaluation where you rotate the options A, B, C, D becomes B, C, D, A, etc., and test multiple times.
Okay. That sounds like it would multiply the testing effort, though.
Massively. It increases time and costs k-fold, where k is the number of options. While it's the gold standard for bias reduction, they found that for this large-scale study, the standard non-circular results were consistent enough to rank the models reliably.
So a pragmatic choice given the scale.
Exactly. It still gave them solid comparative insights without blowing the budget entirely.
All right, the moment of truth then. After all this testing, what's the verdict? Has GPT-5 actually achieved spatial intelligence? What did the scorecard show?
Okay, let's break down the key findings. Finding number 1. GPT-5 is the new state-of-the-art. No question. It surpasses both strong proprietary and open source models by convincing margins.
So clear leader of the pack.
definitely. It showed big advantages across most subcategories in benchmarks like sight, mind cube, and stare. And here's something really interesting.
Go on.
In some specific areas, GPT-5 actually reaches human-level performance.
Whoa, really? Human level in which areas?
Specifically on metric measurement tasks, judging sizes and distances that we talked about, and also on certain spatial relations tasks. It also showed substantial improvements on perspective taking.
Okay, that's genuinely impressive. Human level on some core spatial abilities, but I sense another but coming.
You sense correctly. Finding number 2, there's still a considerable performance gap overall. Despite the wins, GPT-5 is still significantly behind humans on most benchmarks.
Especially which types of tasks?
Especially the tougher ones. Mental reconstruction, MR. Perspective taking, PT. Deformation and Assembly, DA. And comprehensive reasoning, CR. They specifically called out the MMSI benchmark as highly challenging, where GPT-5 is far from human-level performance.
So the more complex multi-step or non-rigid stuff is still a major hurdle.
Exactly, which leads to finding number 3. Spatial tasks just seem fundamentally harder for these models compared to other tasks.
Harder than, say, language understanding or general knowledge.
Significantly so, according to this study. The paper notes that NLLMs have reached human level on several non-spatial intelligence tasks tested in benchmarks like core cognition, things like boundary, perceptual constancy, conservation. But SI remains stubbornly difficult.
Reinforces the idea that spatial reasoning is its own beast.
It really does. And finding number 4 ties back to what we mentioned earlier about proprietary versus open source.
Right, the diminishing advantage.
Exactly. While proprietary models like GPT-5 generally lead, that lead shrinks considerably on the hardest spatial categories, MR, PT, DA, and CR again.
So on the really tough problems, everyone's kind of struggling similarly.
Pretty much. Both proprietary and open source models are performing far below human levels there. The papers suggest this is actually a timely opportunity for the research community to push forward using open source models, since the proprietary ones don't have a magic bullet for these challenges either.
Interesting dynamic. Okay, so those are the big quantitative results. But what about the how? Did they look into how GPT-5 tries to solve these problems? Any insights from its reasoning or specific examples of success and failure?
Yes, they did some really interesting qualitative analysis and ablation studies. First, they looked at GPT-5's thinking modes, using that effort parameter. They could tweak minimal, low, medium, high.
And what did changing the effort do?
Well, more effort generally meant more reasoning tokens, as you'd expect, and accuracy generally improved going from minimal up to medium effort. So more thinking helped, up to a point.
What about the high effort mode, best accuracy?
It had the best raw accuracy. Yeah, almost 69% when they excluded timeouts.
Yeah.
But it came with substantially higher time and compute costs.
The trade-off.
A major trade-off. And it had a high risk of the reasoning becoming too long, hitting token limits or timing out.
Yeah.
In one test, 28 out of 118 questions timed out in high mode.
Ouch. So, practically speaking.
Practically, medium effort seemed to offer the best balance between accuracy and cost reliability.
Good to know for anyone actually using these models.
Yeah.
What about specific examples? Where did it shine or faceplant?
Okay, looking at the qualitative case studies, figure 3 in the paper. For metric measurement, like estimating the garage door height, MM1, GPT-5 was reliable. It guessed 2 meters, the actual was 2.7 meters, pretty close. Shows basic real-world size knowledge.
Good start, foundational.
For mental reconstruction, MR, it was a mixed bag. Strong on reconstructing from multiple views, MR2, the engineering drawings. Also good at null view generation, MR3, the top-down view, if the thinking mode was on. But it was very sensitive to prompts. And it failed that simple block top-down view task, MR4. Answered A should have been B.
That's the baffling one again? Complex, okay. Simple, not okay.
Exactly. For spatial relations, SR, generally well addressed, but with blind spots. Remember the clock versus the house in the background height task, SR5.
Yeah, which is higher in the real world.
GPT-5 said the clock, likely because it looked bigger due to perspective. The house was actually higher. He got fooled by the visual illusion, showing a lack of robust understanding of how perspective affects apparent size versus real size.
Can't separate the 2D appearance from the inferred 3D reality.
Seems like it. For perspective taking, BT, it struggles to reason between changing camera viewpoints, especially with little overlap. The video camera movement task, PT sensed that it's a right ground truth was left.
So it misinterpreted the rotation.
Yeah, its reasoning showed it tried, but fundamentally misunderstood the perspective shift. Not a solid ability there yet.
And the folding and assembly, DA.
That remains a critical weakness. It failed the 2D net to 3D cube folding task, DA7. Failed assembling two L-shaped blocks, DA8. Really highlights its limitations in reasoning beyond rigid shapes.
Okay, so manipulating shapes mentally is still really hard for it.
Very much so. And finally, comprehensive reasoning, CR. It struggles with multi-stage tasks needing memory. Counting the occluded blocks, CR9.
Where it had to infer hidden blocks.
Right. It counted the visible ones okay, but consistently failed to infer the hidden ones, guessing 9 or 10 when the answer was 8. It just didn't see what wasn't directly visible, spatially.
So putting it all together, GPT-5 is definitely pushing the boundaries, setting new records in spatial intelligence, but that human-level grasp of space, especially the complex, dynamic, inferential parts, still a ways off.
That's the takeaway, yeah. This deep dive really shows that spatial intelligence throws up these unique challenges. Even for our best models, there are fundamental gaps. The progress is amazing, honestly, but those limitations in reconstruction, deformation, perspective, complex reasoning, they're significant.
It really makes you think. If even GPT-5, arguably our most advanced AI, struggles to mentally fold a simple cardboard net into a cube, or can't reliably infer a hidden block behind others, what does that say?
It says there might be some fundamental knowledge or maybe some architectural innovation that's still missing. Something needed for AI to truly get the physical world the way we do.
How far are we then from an AI, maybe an embodied agent that can just seamlessly navigate a messy room, understand how objects interact physically, anticipate how things might move or change shape, knowing not just what things are, but how they exist and relate in 3D space?
That's the million-dollar question, isn't it? Or maybe $1 billion given the field. It's clearly a challenge that's going to keep researchers busy for quite some time.